In this video, we're going to use what we just learned about limits in order to explore what it means for a two-variable function to be continuous. So we know geometrically for a function of one variable that continuity meant the function had no jump or holes in the graph. The idea is similar in 3 dimensions or for 2 variables. Here for surfaces, continuity is going to mean the graph fits together smoothly at any given point. We're going to test for continuity using limits. And the reason this is important is because a lot of the theorems and ideas that we're going to use later on require continuity to work. Let's start by defining continuity at a point. So a function is going to be continuous at the point AB if the limit as xy approaches AB of f of xy is equal to f of AB. This requires 3 things to be true. First, we have to be able to evaluate f of AB. In other words, AB must be in the domain of our function. The limit itself must exist, and the limit value and the function value need to be equal to one another. So we have a 3-condition checklist for continuity. A function is going to be continuous at the point AB if f of AB is defined, the limit as xy approaches AB of f of xy exists, and the limit as xy approaches AB of f of xy is equal to f of AB. Once we've established continuity at a point, we can think about continuity on a set or on a region. So we'll define f as continuous on a set S if it's continuous on every point of S. So for any given region, continuity must hold at every interior point. And if we look at the boundaries, we're going to examine those limits by taking paths that are along the domain of the function. As we examine functions for continuity, we're going to take a few facts as true. First, polynomials in xy are going to be continuous everywhere. Rational functions, root functions, trig functions, inverse trig functions, exponential functions, and logarithmic functions are all going to be continuous on their domain. This means that we can boil down most questions of continuity to whether or not denominators, radicals, and logs all give us valid function values. We can also algebraically combine continuous functions, so the sum and product of 2 continuous functions remains continuous. A constant multiple of a continuous function is continuous. And the quotient of 2 continuous functions is going to be continuous, assuming that the denominator function is non-zero. We can also extend ideas of continuity to the composition of functions. So if g is continuous at some point AB, and f is another function that's continuous at g of AB, then when we compose them, f of g of xy is going to continue to be continuous at AB. So in other words, if the inside function is continuous and the outside function is continuous, then the composite of those is going to be continuous. This will help us out a lot when we're looking at trig, exponential, and root expressions, but we have to remember that the domain still matters. In other words, if we're composing a square root function with some other function, the inside function still has to generate non-negative input. This gives us a process for determining whether or not a function is continuous. First, we have to check whether the function is defined at the given point. Second, if it's a polynomial, we get continuity for free. Third, if it's one of our familiar functions, rational, root, trig, logarithms, etc., we're just going to check that the value is in the domain and then conclude continuity based on that. If it's a composite, we're going to check that the inside function is continuous and that the output is in the domain for the outside function. If it's piecewise or suspicious, we're going to have to look at the limit in order to examine whether or not the function is continuous at the given value. All right, let's look at an example. We're going to examine whether or not the function f of xy equals the square root of 4 minus x squared minus y squared is continuous at the point 1, 1. So notice that this is a composition. We have the inside function 4 minus x squared minus y squared and the outside function square root of that. So what we need to know is Is the inside function continuous? So the inside is a polynomial. That is definitely going to be continuous at 1, 1 because it's continuous everywhere. Now we need to ask ourselves, is the outside function continuous? Well, for that to be true, we need 4 minus x squared minus y squared to be greater than or equal to 0 at 1, 1. So that's the question we need to ask. So we'll plug in. We get 4 minus 1 is equal to 2, which is in fact greater than or equal to 0. So we are continuous in our outside function, and so the answer to this question is yes. Let's examine this new function, f of xy equals x squared plus y squared over x minus y, and see if that is continuous at 1, 1. Well, if we evaluate f of 1, 1, we get 1 plus 1 over 1 minus 1, which is 1 over 0, which is undefined. So we can stop right there because a function cannot be continuous at a place where it is undefined. This fails the first step of our 3-step check, and so this is not continuous. All right, our last example is a piecewise function, which means that just plugging in isn't going to work. So here we're going to go through our checklist. We're going to check, is f of 0, 0 defined? And it is. The piecewise function gives us that it is 0 there. So we've got the first test. Now we have to look at, does the limit as xy approaches 0, 0 of f of x, does that exist? This is actually a limit we've seen before. We're going to use the squeeze theorem. We're going to see that this function, the absolute value of this function, is exactly equal to x squared times the absolute value of y over x squared plus y squared, because every other term is positive. And because x squared plus y squared, or because x squared is necessarily less than or equal to x squared plus y squared, this function is less than or equal to x squared absolute value y over x squared, which is equal to the absolute value of y. This limit is 0 as we approach 0, 0. This limit, as we approach 0, 0, is also 0, which forces our original limit of f of x to also be equal to 0. So this limit exists, and the limit is equal to 0. And our last check is, does the limit of f of x as we approach the point in question equal the function value? I should be writing f of xy in all of these. I hope you'll forgive me for that. And the answer is yes, because 0 is in fact equal to 0. So the limit value and the function value are identical here, which means that the answer to our continuity question is yes. Summing up what we've learned, continuity at a point AB depends on the limit as xy approaches AB of our function equaling the value of the function at that point. This means that we can use 3 conditions to check for continuity. We can check that the function is defined, that the limit exists, and that the function and the limit are equal to one another. We know that polynomials are continuous everywhere, and that most of the other familiar functions we look at are going to be continuous on their domains. Lastly, we know that if we compose 2 functions, if we have continuity for the inside function, and then the function on the outside is continuous for all of the values in the range of the inside function, then our composite function is also going to be continuous. Up next, we'll be exploring the idea of the partial derivative.